You start recording again. Stop. Okay. All right. Okay. So let's start the class. All right. You guys can see everything good, right? All right. I want to make sure before I start. Okay. All right. So last class, we basically finished the discussions around inter-process communication topic, which was the third main topic in this class. So basically, we started the topic by discussing some common concurrency issues in a multi-process or multi-threaded programming environment, a computing environment, rather. So these concurrency issues can be mostly generalized as race conditions and deadlocks problems. Then, we introduced the concepts of atomic operations and critical sections. We talk about using some software solutions for implementing the critical sections. Then, we discussed in details of using some hardware support and programming constructs in implementing the atomic operations and critical sections. Specifically, we talk about using the test and set lock atomic operation from hardware to implement the critical sections. And then we talk about in great length in introducing some advanced programming constructs in semaphores and monitors and using them for implementing critical sections, resource allocation mechanisms, and enforcing scheduling constraints for solving some classic inter-process synchronization coordination problems. We specifically, we talk about two classic coordination problems in producers, consumers problem and the dining philosopher's deadlock problem. So that was just a quick recap on the inter-process communication. So today we need to move on to the file systems. So this is the next main topic, which is probably the last main topic we'll be discussing in this class. We will see if we can have some time to look into the input and output topic before May 7th, and which will be the last day of this class. But let's first look into the file systems. So what do file systems do, right? So essentially, a file system does the organization, right, of your files on a persistent media. So it is essentially about how do we organize and access information on a persistent media. So a file system is a system for organizing and manipulating information that in this class we will talk about organizing information and manipulate information on a hard drive or disk or solid state drive. And then, first we need to look at, what is a file, right? We also need to have some sort of definition for a file, right? So what defines a file? Can somebody give me a quick idea? What's in your view a file is? Anybody? You all use files, right? Every time you touch your computer, you are dealing with some sort of, some form of files, probably. Anyone? Well, I mean, I guess a file in itself is some sort of definition by itself, right? So you can say a file is an abstraction to represent a collection of logically grouped data, right? You could define a file that way. Um, so most files are, I kind of mentioned this before, most files in your system are actually small files in terms of size. So most files in your system, uh, they're small files occupying a small disk space, while a small number of large files actually are occupying the majority of your storage space. So later, we will see how, as a file system designer, you can leverage these stats to design your file system to be efficient in storing and accessing data. All right, so yeah, so I just talked about the definition of a file system. Well, as compared to memory, right, which is a temporary storage that could only hold data when it is connected to power, right? So in uh, conventionally, we call memory like primary storage. Okay, we call memory as primary storage. We call disk as secondary storage, right? So that's sort of the conventions people are using. Um, so memory would not hold data when power is out, right? So, but persistent media can store data without power, right? So basically, the data would be still saved on the persistent media, a hard disk or a solid state drive. Um, uh, the data there would persist through power cycles or crashes, or failures of your system. Um, so what we are looking into in this class about the persistent media, we're talking about traditional magnetic disks, right? Solids and solid state drives. Um, so using Linux or Unix as an example, um, so when a file is made and saved to a computer, uh, information that makes it a file exists as a minimum of three things. Okay, so basically you need to have a path or name to the file, right? Which are schematically represented in the file system. Using Linux or Unix as an example, a file also has its metadata, right? Or you can call attributes, right? So the metadata and attributes of a file in the Unix system, they are saved in what we call index node. It's called inode. Okay, so we will discuss about this inode in detail later in the file system implementation. Um, and the third piece of information would be the actual data blocks of the file, right? So you need to have a name, the path and name, they're sort of the same. You need to have a path or name to the file, and you need to have the metadata for the file, and you need to have the actual data blocks for the file, right? So, and a single file can have many names, paths, and inodes, the index nodes I just talked about, uh, and a set of data blocks. All right. So let's first talk about the file name. All right. So, um, what is a valid name for file, right? So actually, I mean, as an end user, what you're seeing in your system, you're seeing all these files. They're with some names, right? So a file name to the end user actually is simply a convenient, readable kind of a name, right? So, but internally, actually under the hood of the operating system or the file system, each file is actually given an identifier, okay? So each file is represented by an ID. Usually it is an integer. It is what we call file ID, okay? So, so that's with the name. So the next question we want to ask, uh, does the operating system know about the file types, right? You know, for example, in Windows, you have sort of every file has an extension, right? Um, your Word files, they have like a dot, .docx, and also uh, that's in Windows. Also in Mac OS also maintains an attribute called the resource fork, which contains information about what program uh, created the file. Okay, so that's sort of like sort of has an association between a file and an application. All right, so the operating systems normally expect applications to know how to read and write files. Okay, that's actually what Unix relies on. So Unix actually does not, in general, Unix does not know how to associate a file with a file type. It only relies on the application to know everything about the file and how to read and write the files. But in Windows, we know that sort of every file has an extension as an association of the file to a specific program that can read and write the file. All right. All right, so I just talk about these. All right, so next let's look at the file structure. So, oops. So there have been two general approaches people came up over the time on the file structure design. They're unstructured and structured. Okay, so basically the byte sequence, which I list here, the byte sequence is an unstructured file structure. Okay, while the while the record sequence and tree, they are sort of structured structures. Okay, so modern operating systems mostly use the byte sequence. Okay, in fact, all versions of Unix, including Linux and Mac OS and Windows, they use this file model. Right? So most of the time, they have file structure as a byte sequence, which is essentially unstructured. Again, the operating systems rely on the applications to know exactly the structure of the file is, and the applications, they know how to read and write the files. All right. So here is a quick diagram, that shows that each type of file structure I just talked about. So to the left, that's sort of like like a byte array. Okay, so that's a byte sequence. That's what we call unstructured. Um, so, um, like the Word file, like a Word file in Microsoft Windows, the Microsoft Word knows how to access the Word file. And again, in the Mac OS, the Mac OS the Mac OS Keynote application knows how to read and write a Keynote presentation file, right? So having the operating system regard files as nothing more than byte sequences provides the maximum amount of flexibility. Again, user programs can put anything they want, right, in their files and name them any way that they can find conveniently. The operating system does not help. but it also does not get in the way, right? So, all right, so the record sequence and tree sequence file structures, they're the two, there's the two diagrams to the right. The middle one is the record sequence, and the right one is the tree sequence file structure. So they're not really used anymore these days. They were very popular in the mainframe era, the IBM machines era. So I think Microsoft actually I think about like that was a long time ago, a decade ago, they were also using some sort of record sequence file structure for some of the files in the Microsoft file system. So anyway, so record sequence and tree sequences, they're structured file structures. We're not going to spend much time here talking about these data structures. But very quickly, basically, you can think records sequence type is sort of a database record, right? In this model, a file is a sequence of fixed length records, each with some internal structure. Okay, while in the tree structure, the structure is basically what the name indicates, right? So information linkage in the file is connected through a tree structure. Anyway, you can look more into these structures by yourself if you're interested. So, all right. Okay, let's talk more about the file types. Okay, so most operating systems obviously support several different types of files. Unix, Linux, Windows. They all support two kinds of sort of files. Okay, so in general, we can categorize files into two types: regular files, special files. The regular files are generally either ASCII files or binary files. When we talk about ASCII files, we're talking about like a text files, right? So ASCII files consist of lines of text, right? In some systems, each line is terminated by a carriage return character. In others, the line feed character is also used. You guys know in Windows, actually, for each line of text, right? At the end of the line, you have both the carriage return character there and also the line feed character there. All right. But in Unix text file, you would only have the line feed character there. So at the end of the line. So, every operating system actually also needs to identify the executable files. Okay. All right. So, so what are some of the examples of special files, right? So it would be directories. They are they are actually some kind of a special files, okay? The directories, they maintain structure of the file system, actually. But essentially, they're also files, right? They're we'll study directories in detail a little later on, actually. So, and there is some other types of special files, and specifically in Unix, we have these sort of character and block special files. The character special files, they're usually used to model serial I/O devices. Okay, like a terminal kind of devices. So they're related to input, output, and again, they're used to model serial I/O devices. Examples would be, again, terminals, printers, and networks, okay? And the block special files, they're used to model disks, okay? Like why they're called block files, all right? So by block, we mean that the minimal unit of the storage that you could access is a block of data, right? As compared to a character, okay? So whenever you try to read or write, read from or write to the disk, you would deal with a block of data, okay? So normally each block of data you read or write like interacting with the disk, usually it is 512 bytes, okay? All right, so there are other possibilities, you know, so like um, one branch of Unix modeled each process as part of the file system. All right, so you guys can read more on this in chapter 6, I believe. There are some more details on the file formats in Unix systems, okay? All right, let's quickly look into um, a special file structure, like this sort of a user-defined file structure, right? This diagram shows a canonical WAV file format. You guys probably know what WAV file is. A WAV file contains compressed data for an audio stream, essentially. This file structure is essentially the WAV file structure specification from some sort of standard. So here you can see, you know, it has a particular structure, right? Sort of very specialized kind of a format, right? So again, this is from a standard um, for describing a WAV audio file, okay? A file structure, here you can see a file structure is only meaningful, right, to the application that knows how to read and write the file, right? So users are free to implement whatever structure they want within a file, actually. So I won't go through the details here. You know, this is very specific to the WAV file format standard. Okay, just want to show you guys an example here. All right, so we talk about, you know, the file type, the file structure. You know, the next we want to talk about how in general a file is being accessed, right? How a file can be accessed, right? What kind of access mechanisms we want to use to access a file, right? So in general, there are two kinds of accesses you can access a file. Sequential access and direct or random access, okay? So when we talk about sequential access, it's just as the name indicates, right? So it basically, you read the file from the beginning and you read the bytes or records in a file in order, right? The access cannot skip around or read the file sequence out of order, right? So essentially, you have to follow, you have to read the file sequentially, right? So the direct or random access means that you know, you can use direct and random interchangeably. Okay, so when we talk about direct access, that means random access. Random access, that means direct access. I know this term is a little bit confusing. So direct access essentially means you move the file pointer to a desired position and you read from there, right? Meaning you know, the application could try to access whichever the position in the file directly, right? So it doesn't need to read all the bytes before the position it wants to read, right? So basically you seek a position in the file, you move the file pointer there, and you read from there. So direct access is very much necessary in a lot of application contexts, Okay, for example, let's say a library system. Okay, a library system needs to be able to search and access a person's borrowing record directly, right? So meaning, you could, the system can first move to a person's record in the database, then directly access the information there, right? I mean, the system doesn't have to read all the records before a particular person's record before it can access that person's record, right? Um, so so under Unix and Windows, usually the direct access involves, again, first seeking a position in the file, then move to that position, and then start accessing from there. Another way to specify where to start reading is to specify a position in the file for every read operation in the file to start reading at. All right. So later we will discuss and evaluate actually the performance of the sequential and random accesses for different file system implementations. So essentially, we can gauge the performance of a file system by looking into the performance in sequential access and direct access. Okay. All right. So obviously, what kind of operations you can have on a file? I list all these operations here. You guys can look into. These are very obvious, operations you can think of, right? That we can do on a file. You guys can read chapter 4 for details there. Here, I do want to say, programming wise, you guys all know that, for your application to do these file operations, your application often calls some libraries, right? Again, right? So, for example, C standard library, and the C standard library would make system calls to talk to the file system. And the file system would talk to the persistent media, like a disk drive or a solid state drive, through what? Through the device drivers, right? So, all right. So here I also want to mention when a file is being opened, there is usually there would be like a sort of a per process file table. Okay, so each process would track all the files opened by that process. Okay, so for each file, you would have a pointer of that file in the open file table. In this per process file table, the current position in the file, meaning the offset of the file that you're accessing, and the file access mode, right? The read, write, read only, write only, or read and write together. And also the file buffer also is being kept there. So this per process file table would keep those information there. There is for each file, there is also this open file table, like a global open file table, shared by all processes. There you would have all processes that are trying to access a file. Right? You will have the information there in this global open file table. Okay. All right. So next, we want to talk a little about the file attributes. When we talk about file attributes, we're talking essentially some file metadata. Metadata is what? Metadata is data describing data, right? So file metadata is the data describing the file, right? Essentially the file description data, okay? So, so here you can see a list of them, and most operating systems, they use either all these attributes or a portion of these attributes, or some other attributes that I don't list here. And so, you know, all these attributes, you guys probably are familiar with a lot of them, right? So, you know, attributes like owner, creator, permissions, you know, modification or access time, you know, these are all metadata about a file. So we won't go through every attribute in this table. Again, you could take a detailed look later at this table. Also refer to the book for more information. So, all right. All right, let's move on to the directories. As we talk about directories, there are special kind of files, right? So, so from OS perspective, a directory is used to organize the file system, usually in a hierarchical way, right? Again, you know, it's like a tree data structure. You could have so you could have a single level of directory or a tree data structure kind of directory structure. Again, that is a hierarchical kind of structure. Again, for any files, right, directories, there are files, you can have all these operations: create, delete, open, read, close, rename, link, and unlink. We will talk more about link and unlink in a few slides. Okay. All right. This is the picture basically showing you you know, what a single level directory system is and what a hierarchical directory system is. Okay. All right. Let's talk about linking. Okay, so you guys, I think a lot of you must have used this linking. You know, in Unix or Linux, you can use the ln, right? That's the command line you can use to do a linking, to create a link, you know, to a file, right? ln, right? And in Windows, actually, not. I don't think a lot of people know. Windows actually has a similar command. It's called make a link. Okay. All right. So basically, they're similar. It's a similar command in Windows. So basically, the linking command, the linker command can create another file that links to an existing file, right? So in general, there are two types of links. Okay, hard link and soft link. Okay, let's see how they work. Okay. All right. So before we talk about the hard link, let's talk about the file name again. So you can view a file name is a pointer, actually. Okay. So in Unix, each file name, as I talked in the beginning, in Unix, each file name has an inode, what we call index node, okay? The index node is essentially the root node of the metadata describing the file, okay? For now, you just need to know that. So each file has an index node in Unix. So when you move a file name, okay, it does not move the actual data that is stored for that file in the data blocks, okay? When you move a file, okay, say you move a file to another directory, it actually does not move the actual data for that file, okay? I'm talking about the physical data blocks for that file. Only what changes when a file is being moved? Only this inode, the index node, which has the metadata describing the file. Only the index node would change. Okay, so a hard link is the same is same sort of a thing. A hard link points directly to a file's data blocks. Okay, you guys got the idea? A hard link points to the underlying data of a file directly. Okay, so all hard links have an same inode, index node, right? So you can move a hard link and it will still point to the same data blocks, okay, for that file. And you can make multiple hard links that all point to the same data blocks and store them in different directories, okay? So if you delete all the hard links pointing to a set of data blocks, then the data will be deleted. Okay. In fact, in the Unix implementation, that's how the delete is done for a file. It's essentially the delete of a file in Unix is like essentially it would just if you have if the underlying data, if there are multiple hard links to the underlying data, the delete would do what? The delete would simply just delete one hard link. Okay, only when all the hard links are deleted and to that same set of data blocks, pointing to the same set of data blocks, only all hard links are deleted, then the underlying data will be deleted. Okay? All right, so so that's how hard link works. Okay, so they're actually, you can treat a hard link as a pointer to the actual underlying data of the file. Okay, so so that's how hard link works. So, but hard link has a problem that it cannot be used across file systems or devices. Hard links they're not supported for that kind of context. Okay, so so essentially, hard link is a technique that allows a file to appear in more than one directory. Or of course, you can create another hard link in the same directory to a file, and you can also do that, right? So, so that's essentially what hard link is. Okay, so there is how the hard links are being tracked. So there is this reference counting that being tracked by all the file operations related to the hard links. So essentially, for each set of for each actual file, there is a reference count, right? Tracking how many hard links that are associated with this that are pointing to this file. And when that reference count goes down to 0, that means that file will be deleted. Okay, so that's hard link. Okay. So as by contrast, a soft link would be like a shortcut. Okay. So, by the way, I forgot one important fact about the hard link is that the hard link, for the hard link, you cannot actually create a hard link to a directory. Okay. You can only create a hard link to a file. Okay. You cannot create a hard link to a directory. Anyone may have an idea on why that's the case. You cannot create a hard link to a directory. Anyone can give me an idea why that's the case? No? All right, so let's just have a quick explanation of that. So basically, the reason why you cannot create a hard link to a directory is it is to avoid circular links, actually. So think about, you have a directory A, okay? And then you cd a, right? You enter into that directory. Then inside directory A, say you create another, you create a hard link B, and you have that hard link pointing to A, okay? So since hard link, they're essentially pointers, right? Like I said, hard links, they're pointers. So here you essentially you created a circular link, right? So you go into A and you create a hard link B, which points to A. Then what? The B and A, they just pointing to each other, okay? So that kind of circular links pointers, so it's not good. So okay, so all right, so that's for hard link. All right, so let's move on to soft link. So unlike a hard link, a soft link or shortcut to a file is not a direct link to the data itself, okay? But rather it is a short file that contains the text of the file name, okay? Or a location that gives direct access to yet another file name within some directory. So essentially, it's just a shortcut, right? So in Unix or Linux, we call the soft link as symbolic links, right? In Mac OS, it is called alias. In Windows, you can they're called shortcuts. Okay, so the symbolic links or soft links, they have the advantage that they can cross disk boundaries and even name files on remote computers. Okay, so their implementation is somewhat less efficient actually than hard links. That's one of the drawbacks of using the soft links. But soft links, they're essentially shortcuts. Okay. So you can also view a soft link is actually just a shortcut to a hard link. Okay, so so the short link, the soft links, they if they're broken, then you wouldn't. Normally, they're not being tracked, right? The underlying data, the soft links are pointing to, you're not tracking that linkage, right? So if the linkage there is broken, then you would have a broken link, right? So so we could see this a quick example down here, right? So here I used the command line ln to create a soft link, right? To create a soft link. So what is the soft link here? Is this child.txt, right? And then if you try to view this link, soft link, it will actually display the actual file for you, right? This child.txt is actually a soft link to the by.txt, right? So, but if you actually delete the actual file, right, and then you try to view the soft link, and then it will tell you no such file or directory. That means the soft link there is broken. Okay. All right. So so if you try to display the information about this soft link, it will give you this kind of display in Unix. So anyway, so essentially a soft link, just a shortcut, right? If the underlying data is being moved, the soft link will not track it. Okay. Any questions about this? About the differences between hard links and soft links and how they work? All right, I guess this is pretty straightforward. Um, all right, so let's move on to talk about the file system design. Okay, so let's get into the nitty-gritty details of the essence of the file system design, okay? So as a file system designer, you're interested in how the files and directories are stored, how the disk space is managed, and how to make everything work efficiently and reliably, right? So, so you would need to weigh between these considerations I just talked about to decide on trade-offs in the actual implementations of the file systems. So now, so there, as I mentioned, that in this class we will talk two kinds of disk drives. So when we talk about hard disk or hard drive, we're talking about the magnetic disks, right? And of course, the solid state drives, they are sort of a flash kind of drives, okay? So so the magnetic disks, they actually work very differently, right, from the flash drives or solid state drives. Right? So we talk about how the magnetic disks, how they work, right? So often, so it works like you have, so essentially you have a disk head that you need to, when you need to access some information on the disk, you need to first move that disk head to a particular track, okay? So so the magnetic disk is like, it consists of tracks, right? So each concentrical circle here is a track, right? So within each track, you have sectors, right? So each sector, this is a sector, right? So basically how you access the data, say in this particular sector here, you need to move the disk head to that circle first. That circle again is the track, right? So you need to move the disk head to that track, and then you would spin this disk, right? And then you will rotate the disk, and then you will eventually you will the sector you want to access will be moved under the disk head, and then you can read the data from that specific sector on that track. Okay, so that's how a magnetic disk works. So there you can see magnetic disks. They often involve some kind of mechanical delays, right? Or we can call that latency, right? So basically, there are two steps, right, for access to happen. First, it needs to seek the position in the disk, meaning it needs to move the disk head to the track, right, which is the circle, to the track first. That's what we call seek, okay? And after it moves to the right track, then you would need to rotate the disk. That's what we call rotation, okay? So for accessing the magnetic disks, there are two sort of mechanical delays there, latency there, seek and rotational times, okay? When every read or write happens, it involves those two mechanical kind of operations, okay? But the solid state drives or flash drives, they work very differently, okay? So they essentially, for a solid state drive, there's no seek time, okay? There's no such thing you seek a particular track. There's no seek time there for solid state drives, okay? So so for magnetic disk, you can see the majority of the delay or latency actually happens when happens in the seek and the rotational times. Okay. All right. So again, a file system file system design. These are the goals. The speed, the robustness, and security, and these are the goals we need to consider when we design a file system. All right, so we'll talk about each one of these in the next set of slides. So just to key to talk, quickly, in like what kind of operating file systems that are used in different operating systems. So Windows, they have these days they have NTFS, right? NTFS actually has been there for a long time. Linux is using ext3 or ext4 now, and also the XFS which is some sort of the later versions of the Linux file systems. And Mac OS is using Apple file systems. Okay, it's a proprietary file system Apple came up with. There are also some early versions of the file systems for personal computers. I'm not sure if you guys know them, but there are FAT, what we call a file allocation table. The FAT32 file system was about just the most popular file systems among the early versions of Windows. All right, and also the FAT32 is actually these days it is often used for flash drives or SD cards. All right, so let's first look at given a persistent media or a hard disk or a solid state drive, first what would you do? So before you can use the hard drive or solid state drive, you normally need to partition the storage, right? To separate it to a few partitions and created maybe a different file system for each partition, right? And then you probably want to install different operating systems on these different partitions. All right, so partitions they're essentially they're just logical kind of separations of a storage that contain blocks of data. Okay, so and you can, like I said, each partition can be managed by a different file system. Okay. All right, so so how the file system layout is done, okay? So we need to look in detail, of how the layout is done. So first, let's look at an example, how in a traditional magnetic disk, how the file system is laid out, how the file data is laid out on the by the file system. Okay, so so here normally, when you deal with a magnetic disk, the sector 0 of the disk is called master boot record. Okay, here. So this master boot record is used to boot the computer, just by the name of it. Okay, so it contains the partition table when the computer is booted. Okay, the BIOS reads in and executes this master boot record. The first thing the MBR program does is to locate the active partition, okay, and read in its first block from the active partition. That first block is called boot block, okay, and then it will execute that boot block, okay? The program in the boot block loads the operating system contains in that partition, okay? So that's how what we call bootstrapping kind of a process, so that's pretty much understandable. You need to do some self-starting process, right? You need to load the operating system from that boot block, okay? All right, so so in each disk partition, okay, it contains all these different parts, okay? So, so again, we talk about the boot block, and the next would be a block what we call super block. Okay, so this super block actually contains the master record, for a file system. Okay, and it contains information about where to look for other things, you know, the type of file system, etc. So usually this super block, okay, is duplicated, all right, for redundancy, for redundancy scheme. You know, if one copy of the super block becomes corrupted, you still have a second copy to use, right? Because the super block has some very important information about the file system. If you lose this super block, you lose everything on the disk. Okay. So the super block, it contains all the key parameters about the file system, and those key parameters, they are read into the memory when the computer is booted or the file system is first touched. Okay, so the typical information there in the super block includes a number to identify the file system type, you know, the number of blocks in the file system, and some other key administrative information about the file system. Okay. All right, so next piece of information is free space management block. So essentially, that block contains information about free blocks in the file system, right? Later, we will actually look into some quick examples of that. You know, how do you track the free blocks in the file system? Actually, in the memory management, we briefly talk about, you know, how you track free blocks of memory. Right? Essentially, here it's sort of the same kind of strategies. You could track the free blocks in the form of a bitmap, okay, or a list of pointers. We'll show you guys some quick examples later on. So then after this block, then it has this inode block, inodes block, the index nodes, right? Again, I talk about the inodes. An inode is has the description, has all the metadata of a file. Okay, it has the file attributes there, and it has the addresses of the actual data blocks for the file. Okay, those information, they are being captured in the inode. Okay, so the inodes can tell everything about a file. Okay, so after that, you know, it will come to the root directory. Okay, so every file system, they starts from a root directory. Okay, it's essentially the top of the file system tree, right? Finally, you know, the remainder of the file, the disk contains all the other directories and files. All right. All right. Any questions about this? All right. Okay. All right. So let's so for files implementation. So we need to file implementation is we're talking about the actual file system design here on just on how the file is stored in the actual media, how the file data is laid out on the media. Okay, so so there are two main considerations here when it comes to file implementation. One is the file storage efficiency, right? And the other is the file access efficiency. Okay, so what is the file storage efficiency? So probably, you know, it is, you know, it is about, you know, how to efficiently lay out data for file, right? So probably this is the most important issue in implementing the file storage. So it is about keeping track of which disk blocks go with which file, right? So there are various methods used in different operating systems. So what is the right data structure in which you can use to maintain the file location information, right? We talk about the inode, for Unix. That's one sort of mechanism there. We will look into the inode structure in detail later on. So again, the file storage is about how do we lay out the files on the physical disk, right? There are some considerations there. Remember, when we talk about the memory management, we talk about external fragmentation, internal fragmentation, and we also talk about the memory used by application can grow, from time to time. Those considerations, there are also considerations here in the file storage kind of design. All right, so that's about the file storage consideration in the file implementation. And we'll also need to talk about file access efficiency. So we briefly talk about the ways to access the files. There are sequential access and direct access, right? So we need to look into the design that how we assess the performance of the file system in terms of file access efficiency. We need to look into the sequential access performance and the direct access performance, right? To gauge the design of a file access scheme. Okay. All right. So let's first look at the file storage kind of implementation. So the first very straightforward kind of allocation scheme would be contiguous allocation, right? Similarly, as we did with the memory allocation, memory management, you can always start with the simplest way would be the contiguous allocation. So this obviously is very straightforward, right? You allocate consecutive blocks for the files. But again, as we know very well from the memory management, we know this could be a bad idea. Eventually, you would have problems with fragmentation problems of the storage. In this case, it would be the persistent media. So the fragmentation will eventually make the disk unusable, right? As files come and go, created, moved, deleted, or the files, the sizes of the files, they can grow, and you create files, move the files, and delete the files. Eventually, you will have your disk fragmented, okay? And after that, your disk can become unusable. All right, so, but there are actually some access scenarios, some media access scenarios that a sequential access would make sense. I'm not sure if you guys used that kind of access before. A CD or DVD is that kind of access, right? Essentially, you can just lay out everything on CD or DVD contiguously, right? Why you can do that? Why you can just do that? Because a CD access is what? It's basically sequential, right? You essentially, you just have to go from the beginning and read from there, right? So a contiguous kind of allocation would work well with that kind of media. Or, in a lot of backup media, like a tape, right, is sort of this, it works similarly, right? It's sort of uh, you can just lay out data contiguously on a tape because most of the time you only have sequential access to that kind of media. All right, and also very importantly is that those kind of media, usually when you write data to a tape or CD, the data wouldn't normally change, right? After you write the data to those kind of media. Okay. All right. So now let's just before we talk about other file storage schemes, uh, let's stay with the contiguous allocation. We want to assess the performance of this kind of allocation. Uh, like, uh, what, like for sequential access and the direct access, what kind of file access performance this contiguous allocation can give us, right? So who can tell me for sequential access with contiguous allocation, would sequential access would be very efficient with contiguous allocation? Anybody tracking? All right. I need someone to tell me, okay, with contiguous allocation, kind of file storage allocation scheme with contiguous allocation, would sequential access to the contiguous allocation be efficient? Anybody? Well, nobody's talking today. Hello? No. Okay. Well, oh, you don't have a mic. Okay. Okay. I know why. Why is it is not efficient with contiguous allocation? Why it is not efficient for the sequential access? Anybody can tell me? Well, we know, like, as bad as this contiguous allocation is in terms of fragmentation problems, right? But remember, if you have everything laid out contiguously, is it easy? Is it easy to access information that is laid out contiguously? Is it easy? It's pretty easy, right? You have everything like allocated contiguously, right? They're all like one after another, so they're all in the same kind of set of blocks, right? And they're all close to each other, right? So for you to access information that is allocated contiguously, it's very straightforward, right? Right? So for sequential access, you start from the beginning and you just read along, right? They're all data, what? All data are put where? They're all put together, right? Contiguously. You don't have to search for blocks, right, in other places because they're all put together, right? So it's very easy actually to find and access data if the data is contiguously allocated. Okay, that's true for sequential access. For random access, what about random access? So it's difficult to increase file size because of the availability of the contiguous memory. Sure, yes, yeah. I mean, that's definitely the true, Mike. So if you want to grow a file with contiguous allocation, it's hard to do that. Yeah, that's very true. But that's about that. That's the drawback from the perspective of file storage, right? So, but right now I'm talking about file access. That's a very good point, Mike. Uh, so, uh, so, so for file storage kind of consideration, contiguous allocation is really bad, right? Probably the worst allocation scheme. But with this contiguous allocation, the access would be very efficient. right? Because essentially you have every data laid out contiguously. You can easily find the data, right? So for sequential access, you read from the beginning of the data. Everything is just sequentially laid out, contiguously laid out, right? So you do not have to jump to other places to read data. And the same thing is true also for random access, right? So we talk about random access is what? Is essentially you move the pointer, the file pointer to a specific location in the file, and then you read from there, right? So with all the data laid out contiguously, it's also easy to search, to seek a position in the file, right? Because you know, essentially they're all together. You just need to move to a certain offset, right, of that contiguous allocation. Then you can find that position and you read from there. So with contiguous allocation, this is probably the best way for file access, actually. But of course, we can't work with this contiguous allocation because, again, it will give the problem of the fragmentation, which which can make the disk unusable, right? So, all right, so that's contiguous allocation. So next we can talk about there are some flexible file storage schemes we can use to do allocation for file storage, and they're linked list and index. All right, so the linked list allocation is essentially it reserves part of the block to contain the block number of the next block. Okay, so you would end up with a series of pointers. Okay, so let me show you a quick diagram here. So this is how a linked list allocation is done. So, okay, so essentially you start your file block from a particular block, then you just need to have part of that block remember the location of the next block, right? So, and you chain them together to form the allocation scheme, okay? All right, so with this kind of allocation strategy, I don't think can anybody tell me, like, with this kind of setup, will there be any external fragmentation? Can there be any external fragmentation with the linked list implementation? No, right? There's no external fragmentation, right? Because essentially, there could be some internal fragmentation in the last block, right? Right. So let's say, this is a file A, right? So for the first four blocks, um, right? So here, for the first four blocks, they're all being used, right? And just the last block, maybe you would have some internal fragmentation that would not be used there, right? So external fragmentation cannot happen with this scheme, right? All right, I guess we're out of time actually. So, all right, so let me quickly stop the recording here.